So, hello everyone around the world. This is the first session on user interfaces and user experience. My name is Reinhard Bacher. I'm co-chairing this session together with my colleague Norihiko Kamikubota from KAK. I'm from DESI. And it's just to remind these presenters, all talks, that the allotted time is 12 minutes, and the audience should keep the microphones closed. And if you have questions, please use the Q&A facility, either using the Zoom app or via the Hua app. Okay, then let's start. Our first speaker is Lana Abadi. She is from the ITER organization in France. She is a senior database engineer, and she's taking care of the design and the coordination of the data handling ecosystem with a particular focus on data visualization. And she has already shared her desktop, so please go ahead.
So thank you, Chairman, for this nice introduction. So I'm going to give a talk about, I would say, a young project we have developed at THAR. So you see many people involved because actually it's an important tool for in fusion. You will see why. Actually, yeah, we need to collect the requirement and feedback. So it's very important to have a growing committee user. That's why there are many people involved. So let's start about with the challenge and the requirement. So there are different stakeholders and different needs. So we have what I can say 3 categories of people. Plant engineer. So they want to do system investigation, research, quick search. You have the science people who are going to do more pulse analysis, research, quick search, and publication. And operation team, which will do pulse analysis, but not as in-depth as science. And they want to do a quick search. So like any other scientific facility, we have heterogeneous data to be visualized. But in our case, it's mainly time series. So we have time and profile traces, we have spectrum, we have fluxes with image, video, but it's always against the time. The architecture needs to be flexible because like many other institutes, we have the project is supposed to last very long. So we need to be able to replace one part without redoing the whole architecture if possible. And like many facilities also, we have 2 sets of tools, web-based tool and desktop tool. In this talk, I'm going to focus on the desktop tool, but we also have web-based application. So it's not only this. So how we started actually the development of this tool. So what we did is we started to see, okay, what the other tokamak are using to visualize data. So in tokamak operation, it's when you for fusion, it's a little bit different. So when you operate, so people start a pulse, and what they want really to see is while you're running a pulse, which could be 5 seconds or maybe longer, depending on what you're doing, they want to be able to plot while actually the thing is going on. And you have 2 types of system. You have what we call system, which are pulse-based, like the heating, neutral, and some diagnostic. So they really do the acquisition during a time window. And you have continuous system, like a cryo cooling water system. And this, they always produce data. And sometimes you need to make correlation between these 2 systems. So having said that, we started to say, okay, the other tokamaks, they always have different family, one for pulse system and one for continuous system. But for ITER, it doesn't fit our need. Then we looked in depth, it's IDL, and IDL is very expensive. And we say, okay, we found one tool which could be interesting to extend, was Thermavic from CEA. This Thermavic was mainly used for image and infrared acquisition. It was C++ Qt, so we say, okay, let's try to extend it to use our unified data access. And we ended up to have something like that. So it looks nice for an engineer. we had the possibility to grow the list of signal, and you could do many plots. We could do many things, move around, zoom, crosshair, and all that. So when we did this development, it was really agile development. We really focuses on performances and resource check, mainly the CPU and memory, because from experience, if you don't pay attention, you can have a tool which are very memory consuming and CPU. We made a demo to the various stakeholders, operation, science. Some were very enthusiastic, but some, mainly operation and science, they were a little bit saying, well, it's okay, but you could see that it was not okay. So we consider that we failed with this tool. And actually, the plus is it was a good way to start to capture the requirement, because when you ask people, it's difficult. It's a very difficult exercise to write down the requirement, especially when you don't really have a machine really, running. So it was quite difficult. So with this prototype, we started to study why we failed, and it turned out that the architecture was not really thought carefully. This is always the problem when you do agile development sometimes. The data access was not fully decoupled. It was fully integrated in the tool, and if you have to develop a plugin for another data source, it would have been a nightmare to maintain. Also, the human factor was not carefully thought. So here it could look nice, but actually the basic operation like overlaying, pulse, and all that, it was taking too many clicks compared to the standard tokamak tools. So after a series of meetings, we say, okay, we better redo the tool. But let's try really to understand better the human factor here, and to have also a better architecture. So what we did is instead of going for C++, we go for Python, because first science really like Python, and we could do Python. There was nothing which would prevent us from doing that in Python. So what we did is we go for a modular approach. We clearly separated the plotting part from the processing, from the data access. The out of scope is, of course, the 3D. And what we did is we developed a plotting library interface, not to OpenGL level, you will see later in some slides, so that people can develop their own tools and applications, and we can have all the same look and feel. With this, we have different need to develop different tools. I will explain which one. And what it turned out that the tree having a list of signal is not maybe the best, because in our case, we have 5 million signal, and browsing 5 million inside the tree is rather difficult. Instead, we realized that it was better to have a tabular view, because people usually, they really know their list of signal. They configure, like they specify the list of a signal list, and then they just load that, and then they always plot more or less the same signal. And then we can also define standard set. We had also discussion about detached and fully integrated panels. So for an industrial system like cooling, cryo, they prefer integrated panel. It's more like close to the SCADA system, but for other, it's better to have, for scientists, diagnostic, they prefer to have detached so that they can move around their panel, and the community approach. So we ended to have 3 types of tools. We focus on the first one, the other are not developed yet because of priority. So we started with a trend. We have a name, it's Mint, and mainly the main focus is to view time series by time range for continuous system or by pulse and profile. And we also have a subscription to live stream, so to have real data for real time display. Then the next one will be image viewer and magnetic flux surfaces. So this is an example of other tool in tokamak. So this is what we need to develop. So this is here the surfaces. This is the magnetic flux. So in this tool, for instance, you have a lot of processing. So from the raw, you need to apply some processing, and you need to make some overlay with the geometry of the machine. Yeah. This is another tool from JET. Is an infrared image, and here typically you have the image, and you need to be able to select a region of reference, and you need to make some correlation with 1D. This is what we need also to develop. So regarding the architecture of Mint, this is the first tool we started to develop, this is a different 4 Legos. So we have the iPlot, which is responsible for the drawing, canvas, plot, axis, and signal. Then it has a link to the data access to be able to retrieve the data. It could be your data or data archive or anything. Then you have the processing layer where, because sometimes you need to apply some transformation to your signal, basic scaling, for instance. And all of them are using the logging libraries mainly to be able to have a common logging format. And then you can build many applications. So for instance, Mint is one of them. So we demonstrated to make sure that our data access is okay. We have we have taken another data source, not only data access for our experimental data, but we have also tried to plug it with the scientific data model. It's called IMAS. And then we also validated our new plotting library by implementing two backends, Matplotlib and BTK, so we can switch between the two. And then we have also developed our processing layer, and this is in development to add more complex processing, many combination of signals. So this is the first. So this is a list of features that has been developed for the first release of Mint. Mainly be able to view one or several trends, pulse-based.
2 minutes
and
left. Please make two minutes left. Okay.
So this is a different feature, crosshair, be able to support envelope, full mode, streaming. This is basic. So the development, the technology behind is Python 3, PySide. We are studying. So what is important here is we have high resolution data, for instance, 100 up to 1 GB per second. So what is important is when you zoom and pan, you cannot retrieve all the data. It's too much. So what we apply here is a technique like we do interactive zooming and panning. So we start with a few points, and the more you zoom, you get more points. So this is an example of screenshot what type of layout you can do. This is more canvas because people want to be able to plot 100 signal. It takes roughly here 2 minutes. Then this is an example of the plotting library, how you can use our library. It's rather simple. So you have canvas, plotting, and you can embark that in a Qt widget. And the main thing where we had spent a lot of time is to be able to support nanosecond, because if you try to plot nanosecond with Matplotlib, it doesn't work because it doesn't work out of the box because of the unsigned 64. So we have to play a little bit to be able to view and analyze sample where it requires nanosecond precision. So the next step is to extend to really work on the code quality, to extend the tool with more feature, be able to process multiple variables, to be able to browse over pulses and variables, and to introduce the new tab surface histogram contour, and to support also overlay in case of XY plot. Yes, I think that's it.
Okay, thank you very much for your presentation. Are there any questions? Okay, I see one question, two questions, obviously in the HUA, the QA even more. So the first question is, have you evaluated the possibility to use diadem tool from National Instruments?
National Instrument from LabVIEW, you mean?
It's called diadem. I don't know what it is. A tool from National Instruments.
No, alors I don't know this tool, but the problem is we cannot use the proprietary tool.
Okay. The second question. Yeah. Okay. The second question is: do you have already implemented the VTK backend?
Yes. Yes. If you look at the paper, we have put a screenshot of Mint with Matplotlib backend and with VTK backend also.
Thank you. And there's a third question in Hoover. Is iPlotlib an ITER development, and next and an additional question, is it available?
Yes, for me it's open source. We can make it available for other people if they're interested.
Good. And here's another question on Zoom. What is the performance of high frequency plotting of thousands of points?
Yeah, that's a good question. Actually, the limiting factor is not the tool itself, because it's okay with VTK, Matplotlib, it's okay. We spot a few things. If you have more plot like that, the key point is the data access. So our data access is all this logic I mentioned for when you zoom and pan. The tricky part is on the data access. So the data access, actually, what we do is we archive the data, but while we are archiving the data, we store multiple resolution of the data so that when we zoom, we are much faster. So we store already down sample while we are doing the acquisition, because we have a requirement that while we are running, we need to be able to view the data. So the zoom and the pan is the key is on the data access. The tool where we see performance thing is this. So for instance, if you want to, here I've hided the legend, just to hide the legend on all this in Matplotlib, it takes a few seconds, whereas in VTK, when we made the text, it's milliseconds, it's much faster. Okay,
we have much more questions. Please maybe have a look to the Hoover, also to the chat. Unfortunately, our time is over for this presentation. And now we have to once again thank you very much. And now let us switch to the next speaker. Norihiko, please, for your introduction.
Yeah, so it's Norihiko Kamikubota, KK. I'd like to introduce the second speaker, Stuart Fisher, European Synchrotron Radiation Facility, Grenoble, France. He is a software engineer in the beamline control unit. He is responsible for coordinating the UI delivery from the acquisition side for new projects. And he has been involved in developing the Dakiri logging library. So his title, talk title is Dakiri, a web-based user interface framework for beamline control and data acquisition. So please start.
I hope you can hear me. Hi to everybody, and thanks to the organisers for letting me speak to you today. I'm going to give you a really quick overview of the Dakiri framework that we've been building at ISRF for acquisition and beamline control. So it's best to start off with what Dakiri is not, which is it does not provide a scan engine and it does not provide a control system. We interface with those through things that we call actors, which execute tasks, and we can get information from the scan data engine using the interface. We then have a really thin hardware control abstraction layer, which we can interface with a control system. So we're agnostic in terms of control system. Core of Dakiri is split up into 3 projects. We have Dakiri, which is a Python server, and that exposes a REST socket IO API. Then we have a JavaScript client, which consumes those APIs, and that's written in React and Redux. And then we have a local project called Dakiri Local, and that's deployed on each beamline. That's a cookie cutter project, so you cookie cutter it, and then that stores things like the config files for the beamline and local implementation, such as how this beamline interacts with the control system, how it launches scans, stuff like that. The architecture is nothing new. This has existed for a long time. MXCube has been doing this for a long time. We have a server, we have a client. Like I said, it talks REST, which is JSON. The client makes requests to that. We can push events from the server to the clients using WebSockets, and this is encased in JWT. We're multi-cliented, so we can have commissioning, acquisition, and we can view scans. Multiple people can be logged in. The server is made up of various little blocks. We have authentication. At the moment, this is LDAP and will soon be SSO. We interact with the database so that we can store information from the user office system. The way people log in is that if they have a valid beamline session, they can log in. The server consumes all of the resources from Dakiri Local. So this has its actors, which talks in our case to our control system, which is Bliss, and the configs in here and the layouts. We then have modular series of components that can be loaded on a per beamline basis. So we have like queues, scans, 2D viewer, and then we have a really thin abstraction layer out to the control system. So that in our case is Tango and Bliss, but you can imagine putting epics in this box as well. So why would you do things like this? This is because we completely decouple the UI from what's going on underneath it. We can consume that REST API with other clients as well. We're essentially platform independent in this architecture. You have to install the server somewhere, but then as long as you've got a modern browser, you can use this UI anywhere you want. The server client API is well documented. If the client crashes, everything's on the server. And ultimately, if the server crashes, most stuff is also persisted in the database. So you don't have to worry about if your client crashes, you lose your list of like queued data collections. And really the primary bonus of this is that we have remote access and monitoring. A dedicated web application will always be more responsive than other remote desktop utilities such as Guacamole and NX. So this is what it looks like on ID21, where we've built the first prototype. We have a common layout renderer at the top. These things are common to all beamlines. So we have what the beam current is, important things that you want to know about, whether the absorbers are open, things like that. We have some common off-screen panels up here. And to the side, we have a list of queued actions, sample information, data collections that have happened. Here on ID21, this is a live stream of the video stream of the sample, sorry, onto which you can click to move around. You can mark regions and points and lines. That's what this panel here is, all the things you've marked. To those points and regions, you can then include data collections. Daiquiri will run those, and then you can generate maps from those data collections and re-annotate those back onto here. So here's a map that's been collected on this particular sample, and if you look carefully, there's a higher resolution map below it here. We also have a series of monitoring bits, so we have motors that we can move around, we can change the zoom level, we can interact with the camera, change the backlight, things like that. This layout render is dynamic, so now we can switch again to another layout, and now we go to commission interface. This is a synoptic of the beamline. You can click into, say, the slits, for example, and show the 4 motors that make up that slit. You can interact with those. We can change the beam viewers, we can interact with the front end, and again, a load of motors and stuff we can move around. We can change again, and now we can go and look at data from a scan engine. So here we interact with Bliss. You can see the list of scans that have been executed on this beamline. We can get 0D, 1D, and 2D data. And this is watching events from the scan engine as well, so this will be updated in real time. If you run a scan, you'll be able to see this update in real time. So the server is written in Python, as I said, gives REST and socket IO. We are geovented because we use Bliss, but Matthias tells me that this should play nice with async IO as well if you're using that. So that's fast, RESTful, and socket IO. We marshal out and in everything that comes in and out of the API. So that's basically validation. You're saying what you want your parameters to look like and what the parameters you spit back out should be. The benefit of that is that we can translate that schema into JSON schema, and then you can consume that in the client as well. So we have a single point validation for what the parameters are, and that can be used both in the client and server. Because we use schemaing on the API, we can use Flask API spec to automatically convert that into documentation of the API. So we don't have to worry about writing documentation from the API. You can inject metadata into this schema, and that will automatically come through into documentation. Like I said, we have component-based architecture. You can choose what things to load on a per beamline basis, and we have interfaces to interact with the scan engine and the hardware layers. We impose a load of core level concepts for an acquisition client. We make people log in because it's a web application, and that means we know what they can do and where we can limit specific hardware to certain people and certain types of scans to certain people. We make you select a session, like a valid beamline session. That's our primary authentication of whether users can access the interface. And that means we can automatically decide where to save the data somewhere sensibly. I said that multiple people can log in. That's not actually a benefit in terms of beamline control. You don't want multiple people moving the beamline simultaneously. So we have a fairly classic pattern system of control request response-based system. So staff can always take control of the beamline, but users must request it. We can mirror session information from the clients too, so we can see what they're doing in case we need to help them. We have an action queue, so we can execute actors sequentially, i.e. run the beamline overnight. And we have ways to store metadata because we have to store some information from the user office, and our control system stores data transiently. Not all scans are available for all time, so we store where the HDF5 files are, for example. Clients written in JavaScript. We use a pretty standard ESRF stack, which is React, Redux, Bootstrap. Then we use Fabric and some other bits. And as I said, this has got a dynamic renderer with some common panels. Layouts are written in YAML and they're nested. So you just put rows and columns and containers together. That maps to Bootstrap's grid engine, if you know about that. And then into that hierarchical tree, you can drop our components, which are like a renderer for a series of motors or the synoptic view or that 2D view I showed. We've also got some templating for this as well, so you can reuse bits of these layouts on multiple beam lines. Schemas and forms. So I said that we use schemas for all inputs and outputs. The actors that execute the tasks on the beam lines also have schemas. And what that means is that control staff can write Python like this. And on the client, this gets transformed into a form which the user interacts with. So that means that beamline staff can develop things in Python without having to know too much about the JavaScript side. In terms of the global infrastructure, Daiquiri, I said, talked to this Maria database. This is actually a copy of some of the ICE/B tables, if you know what that is. And that means we can use other bits of ICE/B infrastructure, for example, to passively monitor the beamlines. So Daiquiri might be doing data collections. You can see what Daiquiri is doing by looking at it in SyncWeb, so without interacting with the control system. We can also take advantage of Zocalo, which is Diamond's automatic data processing framework. Daiquiri also knows how to talk to this with ActiveMQ. So Daiquiri can subscribe to its own queue here, and Zocalo does too. Daiquiri says, I'm doing the data collection. Zocalo says, oh, I need to process that data. I'll go and do that. It writes the results back into the database. It sends a message back to ActiveMQ, and Daiquiri knows that the processing is complete. And this way, it can then read the data back from the database and share in real time as things are being processed. Some links to those below. The whole project is containerized. So everything's in a Docker container. That's my day-to-day development environment. So there's a Docker with Daiquiri, its UI, Bliss, a test session so that you can interact with some simulated motors, writer and some other useful bits and pieces. And we have a pre-populated test database, which you can spin up. Those are both freely available on Docker Hub. At the moment, this is in production on 2 beamlines. So that's ID21, where we do XRF mapping. And it's on BM29 doing biosacks. There it has a custom front end, which has been built specifically for that. And that's because it has a very specific interface, which we want to be consistent with MXQ. We have installations on these other 4 beamlines. 2 of these do simple things, basically monitoring at the moment, just looking at motors. But we're developing more complicated interfaces for BM23 and ID13. And we're deploying this to another 3 beamlines in the future too. I've tried to put all the links to useful things. This is a very quick overview, and you might want to read more about this. There's a landing page which gives you information, a more detailed picture of the project, source and documentation. And there are a load of helper projects that go with this, like the streaming video, generating those synoptics you could see. And that will hopefully become a working DOI to the reference paper that should be out next week or the week after. Acknowledgements, we're a small group in the UI group. There's 3 of us working on this at the moment. We've had help from the DAU for some of the maths for transforms and things like that. And the BCU is a big group. We're 20 or so people. My boss's boss, and many other people have contributed. MXCube is a large project on its own, and there's a big group of people that work on that. And I discussed quite a bit with Jake Phillip from Diamond about GDA and its mapping perspective. We stole lots of ideas from them. That's about it, I think.
2 minutes left.
Oh, I'm too fast.
I see at least two questions.
Yeah, I can see on Zoom. One question is, do you have statistics about the performances related to the number of variables managed by the GUI?
I don't have statistics about that. Everything's debounced, so yeah, the control system could send 100 events from the control system to the client, which would flood it. They're all debounced on the server side, so even if you have loads of parameters emitting events simultaneously, they'll get debounced to about 2-second interval. So it should stay performant even when there's lots of things that are moving simultaneously on screen.
So maybe the second one. Why did you choose to use MariaDB over other databases like MySQL?
MariaDB is just the commercially maintained version of MySQL now. I'm not sure if anyone is still using, well, I guess people are still using MySQL, but the bits of the ICE/B tables that I copied were using MariaDB already, so I just chose to continue to use that.
Mm-hmm. So web libraries change quickly, how do you anticipate backward incompatible changes in libraries such as React in the long run?
A very good question and is pertinent. This is a big problem in web development in that you think something's available forever and it's really not. It's available for like 3 months and then somebody stops maintaining it and it disappears. We hoped by, I think, again, the SRF policies that they picked React a while ago and they hope that because Facebook maintains it, it will be maintained for a long time to come. But still, upgrading versions between like major versions of React is a bit of a big problem. It does break things sometimes. We just have to hope that they continue to maintain the core libraries we've picked for the future.
Okay. About the Hoover side, Reinhard, can you help me? I have a local problem and cannot see Hoover side questions.
There are no questions on Hoover, as I know. Okay, then maybe we can move to the, if there are no additional questions, we can move to our third speaker. Once again, thank you to Stuart. Our next speaker, please stop screen sharing, Stuart. Okay, thanks. Our next speaker is Mahesh Puna. He is from Baba Atomics Research Center in India. Mahesh is a scientific officer and involved in the development of software for scientific projects. So please share your screen. Okay, perfect.
Do you see my full screen?
Yes, it's not full screen, but we see your PowerPoint display. Okay, now it's full screen.
Thank you. Hello, everyone. This is Mahesh. I'm from Baba Atomics Research Center, BRC, India. The title of the talk is Automated Scheduler Software based on the Metro UI designed for the Mesh telescope. So major atmospheric Serenco experiment, Mesh telescope, it's actually a very high energy gamma ray telescope, which has been set up by BRC at Hanley, Ladakh, India. Its main objective is to study the gamma ray emissions from various cosmic ray sources in the energy range of 20 GeV to 10 TeV. And it has been developed as a distributed control system that consists of several functionally diverse subsystems, like a drive control system, which moves the telescope towards source. And there are also other control system, other subsystems like a mirror alignment system, camera system, and time monitoring system, and data archival system, and a weather monitoring system. So prior to the experiment, the astrophysicist generates the observation schedule, selecting the astronomical sources and the configuration to be used for each subsystem for the experiment. And the scheduler also generates the date-wise schedules and stores in the configured centralized location. The Mesh operator console loads the scheduler file and picking the schedule sources one at a time. And excuse me, I'm just nervous. And picking the sources one at a time. Then the data acquisition is done as per the observation time mentioned in the schedule. And the source coordinates are sent to the, excuse me, sir, I am not able to, I'm feeling nervous. I'm not able to continue further. Okay, I'll go to the next slide. So these form the design basis for my Mesh scheduler software. The software actually should provide the facility for selecting the schedule duration, which could be a day or a duration or a year or up to a specified period. And the scheduler also should provide the default source list along with the azimuth and zenith coordinates. And the software should provide the schedule generation for the selected input configuration. And it should also provide the visible astronomical sources to be observed. And the user should be able to automate the schedule preparation by using a filter set for selecting the sources. So the software also should provide various timing plots for the sun and twilight and moon rise times, depending on for deciding the dark period for the observation. So basically, the scheduled observation is carried out during the dark period. The dark period is actually the time span during which there will be no background illumination from the sun, moon, twilight. And the software also should provide a report generation facility. The software has been developed following a layered architecture, and the presentation layer implements the user interface and the various views and the custom controls. And the application layer implements the core modules of the software, which includes the data dark period calculation algorithm and scheduling, auto scheduling controller, and a filter workflow and a schedule file handler. And algorithm layer implements astronomical algorithms that consists of rise and set time calculations of various celestial objects. So basically the main aim of the layered architecture is to separation of concerns among the components, and each layer defines an interface for the services it requires from the other layers. And so this whole the idea is to make a loosely coupled software. So the following astronomical algorithms are implemented in the software, like calculating the rise and set time for the sun, moon, and any custom source with the defined coordinates, and also calculating the moon phase and calculating the dark period for the selected day. So depending on the rise and set times of the sun, moon, and also calculating the azimuth and zenith values for the given source coordinates. So the astronomical algorithms are implemented following the adaptive design pattern. So this makes the application adaptable to any custom algorithm implementation. And it defines an algorithm interface and makes it adaptable to various astronomical algorithm implementations. So the source list is organized into various catalogs of various types, like optical sources or galactic source or extragalactic or positional source. And each source catalog contains a source list with the positional information, which contains like the right accession, REF declination, and the priority. And the sources are stored in a user configurable report format. And the software also provides a source view, which displays the source visibility, and also the polar view for the azimuth trend. And it also contains the elevation view for the 24 hours. And the dark period also plotted along with the elevation view. So this helps the user to decide the exact time for the observation. So basically the main responsibility of the scheduler software is to enable the user to generate the schedule. So the software provides two modes for generating the schedule. One is the auto mode and there is a manual mode. So the schedule generation is automated by filtering and ordering the sources. And on a particular day, depending on the available dark period, the ordered sources are scheduled, and each source is configured to have a default scheduling period. And depending on the available dark period window, the dark period will be allotted to these ordered sources as per the source configured period. And the auto schedule generation consists of the following steps. First is it requires an input, which could be which consists of the location coordinates like latitude, longitude, and the time zone and day selection and observation duration and the source list. And then the user has an option to select the sources from all the complete source. So he could choose any sources of his interest, or he can choose any category of the sources. And then these complete sources are filtered. So in order to control how the sources are filtered, the source reduction workflow has been created. And the workflow projects the filter results for the intermediate filter result. So each filter, so that user can see each filter output. And so this is how the design for the filter source filtering, which consists of filter container, which acts as a filter factory for creating the filter objects and also for composing the filter workflow. And the strategic design pattern has been followed. So that enables us loading these selected filters dynamically. And this design is actually adaptable to the new custom filters also. So Then there are various types of source filters are used in the workflow. Each filter takes an input from the previous filter and produces an input for the next filter in the workflow. For example, source type filter, which actually the selected sources can further be reduced depending on the source type category, which could be either optical or galactic or extragalactic. And a visibility filter, normally the schedule observation is carried out during the dark period. So all the sources, ordered sources should be visible during the dark period for the selected day. So basically, visibility filter produces a set of sources that could be observed for that selected day. And a priority filter, each source is actually given a priority value, and the sources are ordered based on the priority value, and the user can change the priority value while building the workflow also. And then priority resolver filter, for the same filter for the case where there's multiple sources having the same priority value, which could be ordered based on the criteria. Now here the source set time has been used for ordering the sources. So sources which are having the same priority value, the source which sets first is given the more priority. So finally, then the custom filter. So the workflow provides the flexibility to apply any user-tailored filter criteria. So the user can define any custom filter and load it dynamically through the structured XML schema. So this shows one simple custom user filter having a azimuth greater than 50 and zenith between 45 to 90. And this is the XML expression for the custom filter. So basically, the custom filter help to extend the software to various filter criteria depending on the requirements. And the software also provides manual schedule generation. So first, the sources which are for the selected day, the sources which are having the visibility period and overlapping with the dark period are selected. And for the selected day, depending on the tracking mode, whether it could be oval mode or on-off mode, the configuration is set.
2 minutes left, please note.
So this shows the rise and set time plot for a particular day, and it shows the sunrise times and twilight time and the moon times also. And for it also displays the selected source visibility period. So this helps the user to properly schedule the observation as per the requirement. And this shows the sequence diagram for manual schedule generation. So the software also provides different views for visualizing the visibility and schedule reports. The reports are actually exportable to readable format like text or Excel format, and the visibility report contains the date-wise results that contain the dark period and also selected source visibility. And the schedule file contains the following information like sources being observed and the observation time span, dark period available, and tracking mode. So it's a multi-dimensional data. And this schedule report shows the simple matrix layout where the schedule sources are laid out in a row-wise orientation. But this layout becomes difficult to comprehend as the number of sources and the date range increases. So to get a better insight into the statistical schedule statistics, tree map control has been developed, and the control flattens the hierarchical information and presents the multi-dimensional data. So here the view highlights the source with the highest scheduling period, and as indicated by the size of the block. And also for each source block, also the date on which it has got the highest scheduling period is indicated by the size of the date block, and the color indicates the dark period available on that particular day. So the interface, the schedule interface has been developed following a simple visual appearance and allowing the user to focus more on the content rather than the Chrome. And this user interface design and the custom controls are developed following Microsoft design language. It's actually called the flat design, and which follows a simple visual, simple shapes and colors and icons to create the UI tools and reduce the UI noise in terms of visual effects. And the software design user interface has been developed in the WPF framework following MVVM architecture. So separating the user interface logic from the application logic. So this helps to reduce the software coupling and also improves the software maintainability and testability. Astronomy algorithms are implemented in C# and CLI C++. And this shows one simple custom control where the markers indicate the presence of a schedule on the particular day. So overall, the main scheduler automates the schedule generation through the filter workflow, and it provides an intuitive user interface for scheduling the manual observations. And it provides the various timing plots for showing the available dark period and sun, moon, rise times. And the software design is extendable to any custom developed astronomy algorithms. And it provides a reports view showing the simple matrix form and the data tree view visualization. And finally, the telescope has been operational since 2020, and the scheduler software is being used for creating the observations. Thank you.
Yes, also thank you from our side. Are there questions from the audience? Presently, I don't see anything. No on Zoom, also not on Hua. So once again, thank you very much. Thank you for staying in time. Then we will meet again tomorrow at the same time in the second session of the second UX session at the same time tomorrow. Okay, bye. Goodbye.